question 4, and this one states, if the summation Cn times 6 to the power of n is convergent, then the summation Cn times negative 2 times minus 2 to the power of n is also convergent. Alright, so now let's take a look at the solution, and it's in fact true. And I have two solutions here, actually, two ways of solving this. The first one is solution 1. This involves the radius of convergence theorem for power series. So we can look at it here. So we can see this is the case by considering the radius of convergence theorem from my earlier video, and it's again for power series. These are both power series. Yeah, see how it's the same form. There's a coefficient Cn there, x minus a to the power of n. There's 6 to the power of n and negative 2 to the power of n. Those are both in this form. So let's take a look at this theorem. So for a given power series, just to recap on it, the summation from n equals 0 to infinity of Cn times x minus a to the power of n. So for a given power series, there are only 3 possibilities. So that's the key. There's only 3 things that can happen with power series in terms of convergence. So you have the series converges only for x equals a. In our case, a is 0, so it doesn't apply here. And the series converges for all x, or I. There is a positive number r such that the series converges if the absolute value of x minus a is less than r, and then it diverges if absolute value of x minus a is greater than r. And note as before, so this is only, this part 3 or part I is only for the interval, or where this x minus a, it's less than r. But if x, when x equals to a plus or minus r, so at the actual endpoint, the series might converge or might diverge. That is, no information is known about the endpoint. So when absolute value of x minus a is equal to r, then there's you can't really tell. You have to do that other ways. You can't use this theorem there. So let's take a look at our case. So in our case, the series either converges according to I or I. So 3 i's there, or according to case 2 or case 3. So let's write this down. So we have absolute value of, actually not absolute value, I mean the summation from this one. We'll just write the Cn 6x, and so it's assumed you're talking about from n equals 0 to infinity. So we have this absolute. We just use this symbology without the n equals up to infinity, but that is just assumed. So the summation Cn 6n. So if we have this right here, this equals to, in power series form, this equals to the summation Cn x minus a to the power of n. And in our case, we have, write this a bit neater. We have x is equal to 6, and then the a is equal to 0. So in terms of convergence, we have three possible scenarios. We have I. So I is for x equals to a, but in our case, x is not equal to a because we have 6 is not equal to a, which is 0. So we don't have this. So this is, can't apply the first one. So now we either have the second case, so it converges for all x. So let's go like this. If it converges for all x, this is, I'll just write all x. And this one right here is, true. So this is, if this were the only case, this is true. Yeah, so by case 2, this would be convergent because this one right here, this is all x. So negative 2 is part of x. Or you're going to have, I'll just write or, I'll just put an or we have I, and this is where the absolute value of x minus a is less than r. And in our case, we have absolute value of 6 minus 0, like this. This just equals to 6. So in our case, 6 is less than r. So we have 2 possible scenarios. Yeah, so we have either, instead of putting a check mark, let's put this, either this or this. So basically when this 6, if it's less than the radius of convergence r. So we have 2 scenarios, this or this. And now we compare to the other series. So now we have this right here. This is the summation Cn, and then times it by negative 2 to the power of n. So compare this to the other series. So we have summation Cn. Now we have x minus a to the power of n as power series form. So we have this is equal to Yeah, Cn, or actually write the other way around. So we'll write this one here this way and this way. Yeah, so here I just quickly pause the video and then switch things around. So we have this summation like that of Cn times negative 2 to the power of n. Now on this right side we have this summation Cn times x minus a to the power of n. So then in our case what we have here is x is equals to negative 2, a is still equal to 0. Thus, it converges for 3 cases. So we have I. Let's write I like this. I is when x equals to a, but in our case, x is not equal to a. So it's not equal to a because we have negative 2 is not equal to 0, so we can't use this. Yeah, so we have the other case, so we have or this, or I. So we have all x. So it either converges for all x. Yeah, so if this was true in our case, if this converges for all x, then that would be also true. So the statement would be true, but it doesn't. Well, actually, it ends up being, well, all 3 could be, or these 2 could be true as well. So you could either have x minus a less than, x minus a in our case equals 2 negative 2 minus 0. Like that. So there's the x negative 2 minus 0. This equals to, well, this absolute value of negative 2. That just equals to 2. And 2 is less than 6, where 6 is less than r. So if we have this scenario, this is true. So this is less than 6. Thus, this is true. Well, yeah, so this one or this one would be both true. So the statement is true. So this is true because if this converges, then you either have 2 cases where you have where x, so x is not equal to a, so we can't use that. But if for all x, if it's all x, it converges. Or you have this scenario where 6 is less than r, and 2 is less than 6. So then that converges. So then this is true. Alright, so that was solution 1, and that used that radius of convergence theorem right here. But now let's take a look at solution 2, so solve the same thing, but using the comparison test. So we can also see that the summation Cn times negative 2 to the power of n converges by the comparison test. So first recall the comparison test from our earlier video. So if we have suppose a series an, series bn like that with positive terms. So if you have if bn is convergent and an, all the terms an are less than or equal to bn for all n, then the series an is also convergent. Likewise, if the series bn is divergent and all the terms an are greater than or equal to bn for all n, then the series an is also divergent. So in our case, we can take the absolute value and show that the Cn, the summation of Cn times negative 2 to the power of n converges absolutely and hence converges. When it's absolute convergence, it's also equals to regular convergence. Alright, so in our case, the comparison one, we're going to compare it with this Bn there. So I'll just write this here. So the summation of this Bn series, to make it the same notation as the comparison test, this equals to, write this a bit neater, one more time. Alright. Yeah, this equals to the summation, the one we're going to compare it with, that we know converges. This is Cn 6n. This is converges. So we're given that it converges. Alright, so that converges, and now what we're going to look at is, let's take a look at the other term right here. An right here, and we're going to, instead of just using the regular one, because there's a negative there, we'll just use the absolute value of it. So Cn like this, negative 2n. Alright, so now what this equals to was, well, it's going to be equals to, or actually better yet, just because we don't know what the Cn is, just to be more complete, just to remove that out, because it doesn't matter. It's the same thing as this one here, so it's not going to affect the comparison test. So let's just take the absolute value of that there. So then it's negative 2 to the power of n. So in other words, the negatives, anytime it's negative, it just becomes positive. So this is just equal to 2n, like that. Power of 2n. I just made it like that just because, yeah, the solution manual had this, well, it didn't even say that. It just said it converges absolutely. But I'm pretty sure it's better to write it this way, because Cn could be whatever. But it's the same as this one here. So hence this one converges, and now this absolute one, if you take the absolute value there, this equals to this, and yeah, the comparison test has series with positive terms. So yeah, this one, they just assume this is all positive, even the Cn. So might as well just include that as well. Let's just do that as well. Yeah, so we could actually just erase this and put that over both of these. And the reason is because these both have to be positive terms to use the comparison test, and the solutions manual said to use it. So I'm just going to assume they're both positive. So then, yeah, we're just going to assume that both of these are positive. Yeah, the Cn minus 2 to the power of n, and also this right here. So the Cn times 6 to the power of n. So assume that's all positive terms. So then we take the absolute value of this, then the Cn means it's positive. This one turns into positive negative 2 power of n. Just becomes positive 2 to the power of n. And now, yeah, what we have is now these terms right here, an. Yeah, this an is going to be, well, let's put this arrow like this. An is less than or equal to bn since right here, since the only thing that matters is these two. These ones are Cn's are the same. So since 2n, we'll put this like that, since 2 to the power of n is less than or equal to 6 to the n. The only time it's equal is when you have n equals to 0, because remember n is going to be greater than or equal to 0. If it's n equals 0, then they're both equals to 1. So since this is always less than it, then that means this an is going to be convergent, and in our case, absolute values are going to be convergent. Thus, the summation of the absolute value of Cn n minus and then Cn times negative 2 to the power of n, all absolute values, is going to be this converges. This converges like that. And yeah, so that converges, and so does. So that converges absolutely. Well, this regular one with this is, yeah, without that, yeah, absolute value here. So then this means then they both converge. So if it's absolutely converges, then the non-absolute convergence is also applicable too, and that is true like that. Yeah, right. This also converges. All right, and that's a check mark. So that is true. And yeah, we could read this over here. So since it converges absolutely, it therefore converges as per the earlier theorem from question 6. That was basically if it absolutely converges, then it converges. Very interesting.